Projectiles, horizontal landing, type 4, targets and clearing wall. So in 1992, in question 3, we had a particle is projected with a velocity of 6 root g meters per second at an angle of alpha to the horizontal. And it's projected from a point 18 meters in front of a vertical wall, which is 5.5 meters high. So in part 1, it wants us to calculate two possible values of the angle of projection, which is going to enable the particle to just clear the wall. So let's draw a diagram and set up our table. So we have our particle projected at an angle of alpha to the horizontal at a speed of 6 root g meters per second. And then we have a wall that it is just clearing. And we know that that wall is 5.5 meters high. And we know that it is at a distance of 18 meters from where it is projected. So let's make out our table. So we know that our initial velocity is always written as u cos alpha in the I direction and u sine alpha in the j direction. So in other words, if we're filling in u here, u is 6 root g cos alpha, so we don't know what alpha is. And then in the y direction, it's going to be 6 root g sine alpha. A in the x direction is always 0 when we're on the horizontal. And it is minus g in the y direction, because gravity is acting in the opposite direction to which the initial velocity is acting. So v, we know, is equal to u plus at. So that means that v in the x direction is 6 root g cos alpha, and v in the y direction is therefore going to be 6 root g sine alpha minus g times t. S we know is ut plus a half at squared. So therefore in the x direction we have u t, and then obviously a is 0, so half at squared is gone to 0. And then s in the y direction is u times t, and then a half at squared is going to be minus a half gt squared. Okay, so now we have our table. We have everything for the whole question that we require. And the first thing we want to look at is how are we going to find these angles of projection? Well, we have two pieces of information. We have the distance to the base of the wall, and we also have the height of the wall, and we're told that it's just clearing it. So basically what we know, if we look at our diagram, is that 18 meters is going to be our distance in the x direction, and 5.5 meters is going to be our distance in the y direction. And both of those two distances, s of x and s of y, happen at the same time, in other words, at the time of flight. So if we try and work out our time of flight, first of all, so the time taken to just clear the wall, well, we can say that the distance to the wall, in other words, in the x direction, is 18 meters. So we had 6 root g cos alpha t must equal 18. So that means that the time taken to just clear the wall must be 18 over 6 root g cos alpha, and I can of course simplify that to 3 over root g cos alpha. So that's the time taken to clear the wall. So then if we look at the height of the wall, so sy, we know that that's 5.5 meters at the time, 3 over root g cos alpha. So if I sub my time into my equation, 6 root g sine alpha t minus a half gt squared, I'll end up with an equation in terms of alpha. Okay, so let's simplify this equation. So I can see that g is going to go into, root g is going to go into root g, and then sine alpha over cos alpha is tan alpha. So that gives me, so we have 18 tan alpha. And then if I square out my brackets here, I have 9 over g cos squared alpha. And I can see then that g will go into g once. And if I multiply everything across by 2 there just to eliminate the fraction, I have 36 tan alpha minus 9, and I'm just going to take it 9 outside the brackets there to make it more obvious, times 1 over cos squared alpha is equal to 11. So we need to obviously have this in terms of 1 trig ratio, not tan and cos. So if we go to page 13 in our maths tables, we should see that if we have 1 over cos, that gives us sec. So of course 1 over cos squared alpha will give us sec squared alpha, but sec squared alpha is equal to 1 plus tan squared alpha. And all of that is page 13 in our maths table, so the top of page 13. So that means I now will have an equation totally in terms of tan. In other words, we're going to end up with a quadratic equation. And if we have a quadratic equation, we know we're going to get 2 solutions for alpha, which is exactly what we're looking for. We're looking for 2 possible values. So bringing everything to one side, and I'm going to make multiply across by minus 1 there. We have 9 tan squared alpha minus 36 tan alpha plus 20 is equal to 0. So if we factorise that out, you can use your minus b formula or whichever method you want to factorise. Or I'm going to say here, we have 9 times 20 is 180, and the factors that multiply to give us 180 that out to give us minus 36 must be minus 6 and minus 30. So grouping the first 2 and taking out your highest common factor, and grouping the second 2 and taking out your highest common factor. Well, that gives me 3 tan alpha, leaving me with 3 tan alpha minus 2. And then I have 10 as my highest common factor here, leaving me with 3 tan alpha minus 2 again, which is my highest common factor. And therefore that if I take out my highest common factor, 3 tan alpha minus 2, I'm left then with 3 tan alpha minus 10. So letting both of those equal 0, I can then get alpha on its own. So I can say tan alpha must be 2 over 3, or tan alpha must be 10 over 3. But it doesn't want us to find tan alpha, it wants us to find alpha. So I need to get tan inverse of 2 over 3, which gives me a value of 33.69 degrees. And then alpha is also equal to 73.3 degrees. Okay, so a straightforward first part of the question. Now if we go back to the second part of the question, it says show that the value of alpha is tan inverse 2 for the maximum clearance height. So in the first one, it's just clearing the wall, whereas in the second one, it's clearing the wall and it's clearing it by a particular height, and we need to know what is the maximum clearance height. Okay, so let's draw a diagram to represent that. So we know that it's projected into the air at a value of 6 root g meters per second at an angle to the plane that is horizontal. We know the distance to the wall is 18 metres, and we know the height of the wall is 5.5 metres. So therefore, if it is clearing it, this distance above the wall is the clearance height, and therefore that must be the height at that time, which is SY, and therefore the clearance height is going to be SY minus 5.5. So we know our time taken to clear the wall is 3 over root g cos alpha. So basically, if I work out what is SY at this time, well, we know that SY is 6 root g sine alpha t minus a half gt squared. So by subbing in my time there, and then simplifying, well, I can see that root g goes into root g, sine alpha over cos alpha is tan alpha, so that's 18 tan alpha. And then squaring out my brackets there, we end up with 9 over g cos squared alpha. And we know already that our 1 over cos squared alpha is our sec squared alpha, which is 1 plus tan squared alpha. So subbing in that, we end up with 18 tan alpha. G goes into g. So that's minus 9 over 2 times 1 plus tan squared alpha. In other words, we have 18 tan alpha minus 19 over 2 minus 9 over 2 tan squared alpha. So now we have an equation to represent SY at the point where it is clearing the wall. And we know that the height of the wall is 5.5. So therefore we can say our clearance height let's call it S is going to be SY minus 5.5, so that's 18 tan alpha minus 9 over 2 minus 9 over 2 tan squared alpha minus the height of the wall, which is 5.5. So this is not the maximum clearance height, this is the clearance height. So the max is always found in maths by getting our first derivative. In other words, we're going to differentiate S with respect to the angle alpha. And of course, to find the max, we then let that equal to 0. So let me just simplify this first, because I can add the 5.5 and the 9 over 2 there. So that's 18 tan alpha that's going to be minus 10. So now if I get ds d alpha, well, if I differentiate tan, I get sec squared. And then if I differentiate tan squared alpha, well, it's power trig algebra, or sorry, power trig angle. So I'm going to bring down the power. So that's 2 tan alpha. And then differentiate the tan. So that's going to be sec squared alpha. And then if I differentiate the angle, that's just going to be 1. Now if I differentiate 10, I get 0. Okay, so simplifying that, my first derivative is 18 sec squared alpha minus 9 tan alpha sec squared alpha. So I'm going to let that equal to 0 now. So that gives me 18 sec squared alpha minus 9 tan alpha sec squared alpha. So I can see 9 sec squared alpha is the highest common factor there. So if I take that out, that leaves me with 2 minus tan alpha equals 0. And if I let both of those equal 0, then I get tan alpha equals 2, and hence alpha is equal to tan inverse of 2, which is what I wanted to prove. And over here it's irrelevant. We don't need to do anything with that. So an interesting question that. So always be mindful of this max here. Okay, so the maximum we're looking for is our derivative, and we let our derivative equal to 0. So good clear diagrams should clearly highlight how to work out what that clearance height is.